All right, everyone, welcome back. In this example, we were asked to evaluate the double integral of the function y times sine of x times y over the region R, where R is the rectangle that has x go from 1 to 2 and y go from 0 to pi. And so the point of this example is to see that the order of integration that we choose can actually make a big difference in the amount of effort it takes to evaluate a double integral. All right, so remember, Fubini's theorem says that we can choose the order of integration when we're integrating over a rectangular region. And so we might not have any foresight in this example as to which order of integration might be easier. So let's just go ahead and jump right in. Let's go ahead and integrate with respect to x and then with respect to y. Okay, so if we're integrating with respect to x first, then the inner integral has to have the limits of integration correspond to the x values from 1 to 2. And then our outer integral is with respect to y, so its limits of integration will have to correspond to those y values from 0 to pi. All right, so we're integrating with respect to x first, and that means we treat all these factors of y as if they are a constant factor. And that's going to make our antiderivative a lot easier to find. We can just use a little u substitution, but it's going to be a pretty straightforward u substitution, so I'm not going to write all the steps down, but we would set u equal to x times y to get the ball rolling. And so the antiderivative we should end up with is negative cosine of xy. We're going to have to evaluate this antiderivative at the x values of 1 and 2 before we can integrate with respect to y. And we can always check if we found the correct partial antiderivative by taking the derivative of our antiderivative with respect to the variable we just integrated with respect to. So if we differentiate this function with respect to x, we should get back to y times sine of xy. So we're going to have to use the chain rules to take the derivative here with respect to x. We get the derivative of the outer function, which is going to give us negative cosine. So we're getting back to a positive sign. We evaluate that at the inner function, so that'll give us positive sine of xy. And then to finish the chain rule off, we have to multiply all that by the derivative of the inside with respect to x, and the derivative of xy with respect to x will just give us that factor of y. So we have found a correct partial antiderivative here, and now we have to evaluate it at the x values of 2 and 1. So that'll give us the integral from 0 to pi of negative cosine of 2y plus cosine of y. And so now we're integrating with respect to y. So what is the antiderivative of negative cosine of 2y? It should be negative sine of 2y over 2. Then we have to add to that the antiderivative of cosine of y with respect to y, but that'll just be sine of y. Remember, we don't need any constants in our antiderivative here or any functions of x. We do, however, still need to remember that our limits of integration are pi and 0, and we have to evaluate the antiderivative with respect to y that we just found at our upper limit of integration and subtract away from that our same antiderivative evaluated at the lower limit of integration. Well, if we plug in pi into our functions here, we're going to get sine of 2 pi and sine of pi. Both of those zero out, and sine of 0 will also give us 0. So integrating with respect to x and then with respect to y, we see that our double integral here is equal to 0. And our process here was relatively straightforward. We only had to use a little u substitution really to find our antiderivatives. What we're going to see in just a second is if we switch our order of integration and integrate with respect to y first and then with respect to x, this whole process is going to be a lot more complicated. And a point of going through that is to illustrate that sometimes the order of integration can make a really big difference. All right, so we're running through this example again. We already know the integral is going to evaluate to 0, but now we're going to do it with the opposite order of integration. So first we have to integrate with respect to y, and well, now we have one function of y, or just y, times another function of y, and so we have a product of two functions we are trying to integrate here, and a u substitution won't save us, so we're going to have to use integration by parts. So already we might see the point of this and that, well, this order of integration is going to be a lot more difficult, but let's go ahead and finish it off to really see all the steps involved in this more difficult order of integration. And so we are going to have to use integration by parts here, but we're going to be integrating with respect to y in our integration by parts formula. So I'm just writing up our integration by parts formula as a reference. And so remember, we have to view the function we're trying to integrate as u times dv. And so we're going to go ahead and let u be equal to y and dv be equal to sine of xy times the differential of y. Okay, so the next pieces we need to find in our integration by parts process is the derivative of u with respect to y, which will give us dy, and then we have to use dv to help us find v, and here we can see dv involves a differential of y, so to find v, we're going to have to integrate with respect to y. And we might need to do a separate little u substitution off to the side, but it should be pretty quick and easy to see that the antiderivative of dv being sine of xy dy, the antiderivative of that with respect to y is going to give us negative cosine of xy all over x. And so now we have all the pieces required for our integration by parts formula, but remember, all of this is living inside of our outer integral, the integral from 1 to 2 with respect to x. So I'm putting this big set of parentheses here because we're going to have to throw our integration by parts formula inside of our outer integral with respect to x. Okay, so we're going to get u times v, which is going to look like negative y over x times cosine of xy. And remember, we're evaluating this here, so I guess I didn't write up the integration by parts formula for a definite integral. We just have to throw those limits of integration on there. And our limits of integration for the inner integral are from 0 to pi. And what we have to subtract away from this still, the integral of v times du, and this is still going to be an integral with respect to y. So it'll have limits of integration from 0 to pi, and the function we have to integrate is v times du, and v times du is going to give us negative cosine of xy over x. All right, so now we can evaluate this uv at pi, and let's see, we're going to get, remember, and these are y values here, not x values. That's an easy mistake when working with double integrals, plugging in the wrong values into the wrong variable. And so if we plug in y equals pi, we're going to get negative pi times cosine of pi x over x. Then we have to subtract away from this piece evaluated at y equals 0. That'll give us a cosine of 0, but also multiplied by a negative 0 over x, so that whole thing will 0 out. So we got this nice first piece, and then we have to add to this the integral from 0 to pi of cosine of xy over x. And it looks like I forgot a couple of my differentials, so let me make sure to get this correct and throw them back in there. So remember, this integral was inside of our integral with respect to x, and it is still being integrated with respect to y, so I forgot that differential of y there, and I also need it down here as well. And so now we can find the antiderivative of cosine of xy over x with respect to y, because remember, x is just a constant factor, and this is really almost just like integrating a cosine function. So we're going to end up with is sine of xy over x squared, and this piece we still have to evaluate at our upper and lower limits of integration, which are y values. Then we can combine them with the earlier function we found, and after all that, we can integrate with respect to x. So we still have inside of our integral from 1 to 2 with respect to x, the quantity negative pi times cosine of pi x. Remember, this piece is not involved with this other inner integral with respect to y, so we don't have to worry about evaluating it at those limits of integration. We basically already did that earlier. It came from an earlier piece in our integration by parts process. So we have negative pi times cosine of pi x over x, and now here we can evaluate this at pi. And so let's see, we're going to get sine, and this is a y value here. We're going to get sine of pi times x over x squared, and the lower limit of integration of y equals 0 is going to give us a sine of 0, which just evaluates to 0. All right, after all the work we've done so far, we've evaluated our innermost integral with respect to y, and now have the entire original double integral written as just an integral with respect to a single variable being x. But how are we going to finish this off? Well, we're going to have to do integration by parts one more time. And what we're going to do is we're just going to use integration by parts on this first term, and we're going to see that it actually cancels out the second term once we put it all back together. And so for our second iteration of integration by parts, we're going to let u be equal to 1 over x. Then dv is going to be equal to what's left over for this first piece, which is negative pi times cosine of pi x dx. Remember, we're really just focusing on integrating this first term with respect to x. Okay, then du, would be equal to negative 1 over x squared dx. All right, and so if we anti-differentiate with respect to x, the function negative pi times cosine of pi x, we'll find v, and v will end up being a negative sine of the quantity pi times x. Remember, you can take the derivative of this using the chain rule, and if you take the derivative of this using the chain rule with respect to x, we should get back to dv, or where we started. Okay, so we have all four pieces that we need for our integration by parts formula, so let's go ahead and put them back together. And remember, we're really only applying this to the first piece of this integral, so we're going to have to add on to our integration by parts formula the integral from 1 to 2 of sine of pi x over x squared. But first, let's look at what we get from our second use of integration by parts. So we're going to get u times v. So u times v is going to look like negative sine of pi x over x. We'll have to evaluate that at the limits of integration of 1 and 2. Then we have to subtract away from this the integral of v times du. So what is v times du going to look like? Well, we're going to get these double negatives canceling out, and we'll end up subtracting away positive sine of pi x over x squared dx, and this integral goes from 1 to 2. So this is what we get out of our integration by parts formula. Then we have to remember to add to this that remaining piece from our original integral, and that's going to be the integral from 1 to 2 of sine of pi x over x squared dx. And well, let's see. This integral is going to cancel out that second integral, and what we're left with is just this quantity, negative sine of pi x over x. We still have to evaluate this at the upper limit of 2 and the lower limit of 1, but we're going to get sine of 2 pi and sine of pi when we do that, and both of those are going to zero everything out. So once again, but through a much longer and more difficult path, we have found that this double integral evaluates to 0. So the order of integration does in fact matter and can make our lives a lot more difficult or a lot more easier depending on which path we choose. So if you find yourself setting up a double integral and right off the bat you have to use some advanced technique like integration by parts, consider changing your order of integration. It may make the problem and your life a lot easier.